So it's my distinct pleasure to introduce Nate Kaib, today's speaker. Nate finished his undergraduate at Case Western, a BS in physics, before moving to the University of Washington. He thought he was interested in supernovae, then he could talk to Tom Quinn and got to working on the Oort cloud. I don't know if you knew anything. Did you know anything about the Oort cloud before that?
Oh, no. I mean, I probably had heard of it.
So he's had the opportunity to work with really some amazing dynamicists, starting with Tom. He went, from there he was, went to become a CETA National Fellow at Queen's University, working with Martin Duncan, another person who was like a legendary in terms of our early understanding of the Oort cloud. From there he went to Sierra at Northwestern, and I think mostly worked on his own things.
Yeah.
He was a fellow at the Carnegie Institution of Washington, supervisor with John Chambers. So he's really had this opportunity to work with some of the real pioneers. He spent a good amount of time at University of Oklahoma and took the daring change of leaving a tenured position to join the Planetary Sciences Institute, where he's continued his research. He's been involved in a lot of work that's sort of shown that our solar system is not isolated. It's very much affected by the stars and other mass nearby, and that we've really been sort of making this long-term mistake of ignoring that we are embedded in a galaxy. So you're going to get to see the latest iteration of that kind of work. So take it away.
Oh, thanks a lot for the introduction, and thanks for having me here today. So yeah, the title of my talk is kind of two disparate topics. Field stars, that's what stellar passages refer to, and the orbital evolution of our planets. And this work has been done pretty much completely in collaboration with Sean Raymond, who's a scientist in Bordeaux, France, a CNRS scientist. I think he might actually be the head of the Astrophysical Observatory there now. So that's supposed to happen at some point. I don't know if I let that secret out or not. Not that it matters. So I always begin my talk with a diagram of the solar system because my office mate in grad school, 3 years in, didn't know the order of the planets, which I was always amazed by. But then he works on quasars. He's still an astronomer, and I know very little about quasars, so I feel like it's a good idea to always just give a big picture overview in the beginning of a talk. So this is our solar system. 4 inner rocky planets, Mercury, Venus, and Earth. 4 more massive planets, Jupiter, Saturn, and Uranus, and Neptune further out. And then we have these small body reservoirs, the asteroid belt between Mars and Jupiter, and the Kuiper belt out beyond Neptune, Pluto being the most famous member of the Kuiper belt, I would say, and everything orbits the sun, obviously. And so I'm going to be spending all the time today talking about the solar system. And I'm going to be talking mostly about the orbits of the solar system. And any orbit around the sun can be described with its orientation, shape, and size can be described with 6 parameters. I'm going to be focusing mostly today on orbital eccentricity. And that just measures how circular or how elongated an orbit is. And eccentricity varies it's a number that varies between 0 and 1. So an eccentricity of 0 would correspond to a perfectly circular orbit. And then as you approach 1, the orbit becomes more and more elongated. And 1 is a parabolic orbit. And for an eccentric orbit, so one that's not a perfect circle, the sun doesn't sit at the center, it sits at a focus of the ellipse. And the distance of closest approach is known as the perihelion, or paracenter, more generically the perihelion in our own solar system. So that's all the broad background I want you to remember for this talk. I think it is, at least. And now here's an outline of the more detailed outline of what I'm going to talk about today. So I'm going to begin with just going over some more kind of technical concepts of the long-term orbital evolution of the planets, how we think they generally behave on long time scales. I'm going to talk about how that leads into our understanding of the fact that if you look at the orbital evolution, it's chaotic. There's a degree of chaos amongst the planets and how their orbits behave over time. And I'm going to talk about, following that, I'm going to talk about the role that stellar passages play in the chaotic orbital evolution of the inner solar system specifically. But it really applies to all the planets. And once we finish with that, we'll talk about how passing stars can affect our understanding of the ultimate stability of our planets of the solar system as well. So we'll begin with the long-term orbital evolution of the planets. When I was at OU, I taught Astro 101 a lot of times. You go over Kepler's laws that if you have a planet and a star, the planet moves on a closed ellipse. And so if we look at Jupiter, and according to Astro 101, if we measured its orbital eccentricity as a function of time, you'd expect a flat line that wouldn't change. But of course, if you run a simulation of the solar system and you actually measure the eccentricity of Jupiter as a function of time, it's not fixed. There's small oscillations. It varies between about 0.03 and 0.06. And there's these, this is over a time scale of 300,000 years. So on tens of thousands of years, the eccentricity varies significantly. And the reason for this, of course, is that there's not just one planet in our solar system, and there's other planets. And for Jupiter, the most important one is Saturn. It's its neighbor, and it's the second most massive planet in the solar system. And so because of Saturn's presence, as well as the other planets, Jupiter doesn't just exist in a perfectly spherically symmetric 1/r gravitational potential. Saturn's there adding its own small gravitational field. And as a result of Saturn's presence, Jupiter's orbital eccentricity fluctuates over time. Sometimes it becomes more circular, other times it becomes more eccentric. And now, sometimes Saturn's perturbations drive it towards a more circular orbit, and other times it is driven towards a more eccentric orbit. And the main determinant of whether the orbital eccentricity of Jupiter is increasing or decreasing comes from another orbital element, or really a combination of two orbital elements, which is known as the longitude of perihelion. And so that's basically the angle relative to some fixed direction in an inertial frame, the angle that points towards the perihelion of Jupiter's orbit if you project it down into like the average plane of the solar system. And so this angle, just like Jupiter's eccentricity, this angle, due to perturbations from the other planets, doesn't stay fixed with time. It moves around. And so this is called orbital precession. So the orbital ellipse precesses over time. And when that angle is certain values, Saturn's perturbations cause Jupiter's orbital eccentricity to increase. When it's other values, it causes it to decrease. And so if I change the plot that I just showed you, and instead of plotting it versus time, I plot Jupiter's eccentricity times the sine of its longitude of perihelion on the y-axis, and Jupiter's eccentricity times the cosine of its longitude of perihelion on the x-axis, we get a different, it just looks different, but it looks like there's a clear dependence on the longitude of pericenter. And just to orient yourself, this is effectively a polar plot where the quadrant tells you what the value is for longitude of pericenter, and the distance from the origin tells you what the eccentricity of Jupiter's orbit is. So if you sit right here, you're circular. The further away you get, the more eccentric or elliptical you get. So this was run for 300,000 years, and you can see that there's this clear dependence here. But you can also see that the pattern isn't going to exactly overlap. There's not going to be a repeating pattern. Now, the reason for that is that that was measured relative to some arbitrary direction in an inertial frame. But of course, just like Jupiter's orbit precesses in response to Saturn's perturbations, Saturn's orbit precesses in response to Jupiter's perturbations. And so they're both going around, and what you should really do, instead of, if you want to look at Jupiter's perturbations, instead of measuring the longitude of perihelion of Jupiter's orbit relative to some reference direction, you should measure it relative to the perihelion of Saturn. So when we do that, this plot gets transformed to this, where instead you're plotting eccentricity of Jupiter times sine of the difference in the two longitudes of perihelion on the y-axis and the cosine on the x-axis. And so now things look much more ordered, and you can see that when this angle is 0, that means their perihelion are aligned. Jupiter's eccentricity is at a minimum. It's about 0.03. And then when the perihelion are anti-aligned, that corresponds to Jupiter's maximum eccentricity. which is 0.06. And now you can see how Saturn really controls what's happening with Jupiter's orbit. But you can see that this plot doesn't explain 100% of the story. There's still some scatter in this time sampling. And the reason for that is, of course, that there's more than just Saturn in the solar system. There's other planets that also perturb Jupiter's orbit. And so the angle between those perihelia also matter, and you might imagine little corkscrews or whatever on top of that plot that marks Saturn's perturbations. And the main planet that also perturbs Jupiter is Uranus, but the other ones matter as well. And so there's this slight scatter from the perturbations of other planets. And as I kind of illustrated with this toy animation, Jupiter and Saturn don't precess at the same average frequency or the same average rate. And each planet precesses at a different rate. And if you look at these types of plots, not these, more like this, what you find is that each planet's eccentricity fluctuations can be decomposed to first order into 8 separate eigenfrequencies corresponding to each of the other planets, where each eigenfrequency is associated with a certain planet's precession rate. And so, so in our solar system, Saturn happens to be the fastest precessor. I think it's 28 arcseconds per year. No, that's per century. And Jupiter is on the lower end at about 5 times as slow. And so you have all these different frequencies going on with the orbital evolution of the solar system, and that raises the prospect for whether, that raises the possibility that this orbital evolution might not be regular. There might be a chaotic component to it. And this has been known for 30 to 35 years. So this is an example of those types of plots that you just saw, but made for each planet in the solar system. You can see this is dated. They have Pluto on here as a planet in 1991. But you can see that the behavior of Jupiter and Saturn is pretty regular. You could imagine, I mean, that looks kind of predictable, but then you look at planets like Venus and Earth and Mars and Mercury, even Uranus and Neptune, and they look less ordered. And this paper, as well as a couple others written around the same time, proposed that the dynamics of the planets are chaotic over long time scales. And so I just stole this little animation off of Wikipedia. Another classic chaotic system is a double pendulum. And you can see these three pendula were started with almost the same initial conditions, but not quite. And very quickly, their behaviors diverge. And you wind up, after just a few cycles, each one of these iterations is behaving quite differently. And you can do very similar things with the planets of our solar system to see if they're chaotic. Oops, I didn't want to do that. So instead of showing, marking the position of a pendulum, what we do, what you can do is make plots similar to what I showed you before, where instead of a few different pendula, I have 100 different simulations of the solar system, just the planets, and Pluto. And each one of those 100 have almost the same initial conditions, but not quite. I varied the initial planetary positions by a random number between plus or minus 2 centimeters, which is, yeah. So it's like, like that. So we're never going to know the positions at that level. Yeah, that was probably overkill, but anyways, so that's what I did. And then you run those simulations, and in this particular instance, we were interested in how the Earth's orbit changed in the past. But you can run them forward in time or backward in time. As long as the forces are conservative, the dynamic should be the behavior should be the same going forward or backwards. And then we just sample the Earth's orbit every 1,000 years. And it's shown on a plot similar to what you saw before, where it's a polar plot. Distance away is the Earth's eccentricity. So this is more eccentric, this is less eccentric. And then the quadrant, or the angle of the polar plot, just refers to the angle of the longitude to pericenter of the Earth. And I have 100 simulations, sample them for every 1,000 years, and you'll see that the arc, well, I'll just start it because the movie's kind of boring at first. you're looking at basically 300,000 year sampling every 1,000 years of Earth's orbit. And each individual dot that you see is composed of 100 different systems. So they all lie right on top of each other. They're all given a unique color, but you can only see the last one I plotted, which is red, because they're all right on top of each other for the first 25 million years at least. And so at first it seems pointless to have run 100 simulations of this because they're all doing the same thing. This is where I kind of run out of things to talk about till the movie starts to look cool. But you can just start to see it at maybe, yeah, occasionally the dots start to look a little fatter at 40, 45 million years in. And now you can start to see that things are starting to spread out. And by 50 million years, you can now see all the different colors associated with all the individual simulations. And at 65 million years, I think is where we stop, you can see that those 2 centimeter variations in positions have led to huge uncertainties in what the orbit of Earth looks like at a given time. So each one of these stripes are all 100 different simulations shown at a different time. And you can see that close to the origin right here, those stripes translate into a plus or minus 0.01 uncertainty in Earth's orbital eccentricity. And I can't remember off the top of my head what Earth's orbital eccentricity is right now, but I think it's like of order 0.03. So that's like a 30% uncertainty if you just use its current one as a benchmark. And just to illustrate how this works, these are 2 individual systems, 2 individual simulations out of that batch of 100. And this is Earth's eccentricity, the absolute difference between Earth's eccentricity and realization 1 versus realization 2. And you'll notice that the y-axis is a log scale, and time is shown here in millions of years. And you can see it's pretty much a straight line on a log scale y-axis. And you can also see after about 70 million years, you get to uncertainties that are of order 10% of Earth's mean eccentricity. So Earth's mean eccentricity integrated on million-year timescales is something like 0.03. You approach 10% of that value at this point. And so that's kind of a benchmark that's used in the literature. At that point, you basically stop believing your simulations when their uncertainties approach 10% of the mean value for Earth's orbit. And so these small uncertainties or these small differences between systems grow exponentially with time. This is a hallmark of chaotic dynamics. This was first shown by Lascar in 1989. And it's not just true of Earth, it's true of all the inner planets, and even the outer planets. That's true, but it's more bound in chaos. This is a different thing, or a different talk. But so what the takeaway of this is that you can use simulations to tell you very confidently what Earth's orbit did 1 million years ago or 10 million years in the future. But if you start getting to 50 to 100 million year timescales, you can really only study Earth's orbit and the other orbits in a statistical sense. You run 1,000 simulations and you look at the distribution of solutions that you get. And there's lots of chaotic systems. So I show another one that everybody's familiar with. Local weather is subject to chaos. And so I looked at the local forecast last night. Normally there's better variations than this. The forecast is really boring right now, although it's nice weather. But so if you look at the forecast, I mean, you just intuitively know this. If you look at the forecast, you can base what you're going to wear on whether you're going to bring an umbrella for tomorrow. You're a high degree of uncertainty. If I wanted to base my wardrobe on next Tuesday with this forecast, I really wouldn't do it because you just intuitively know that things can change. And the reason for that, the reason that a 2-day forecast is more reliable than the forecast 8 days out is because we don't know the current conditions everywhere on Earth to infinite precision right now. There's some uncertainty in, I know nothing about weather, but there's uncertainty in temperature, wind, pressure, all those things that matter. And those uncertainties become larger, or the differences between models become larger and larger over time. And so that's why, normally this is a bummer that this worked out this way. But yesterday, the Tuesday's forecast was pretty much perfect, although partly cloudy changed to mostly cloudy. I don't know exactly what that means. But then you can see that way out Wednesday, the high changed by 4 degrees instead of 1 degree. So there's just more uncertainty in the projections as you go further away from whatever your starting point is. And so the Lyapunov time for local weather forecasting is on the order of days. For our solar system, did I explain what the Lyapunov time? That's the time scale at which your uncertainties in your initial conditions grow exponentially. And so the Lyapunov time for planetary orbits is much longer than days. It's 5 million years. And we do know the planetary positions to a pretty high degree of precision, so that it takes a long time for that 5 million years to turn into total unpredictability for what the planets have done. So because of this 5 million year time scale, you can go lots of Lyapunov times before you lose predictive power. It turns out you can go about 60 to 70 million years, either forward in time or backward in time, with simulations to predict what Earth's orbit or other planets have done or are doing at any particular time. So the difference between, or one difference between weather forecasting and modeling of the planet's orbits is for weather forecasting, you can see, for weather forecasting, we just simply write down what the temperature was yesterday or the day before. But what we do with simulations of the planetary orbits is nobody wrote down what Earth's orbital eccentricity was 1 million years ago or 10 million years ago. And so to try to get at the past records, you run a backward simulation, just like you would run a forward simulation. And so that's why you were seeing those simulations run in reverse time, where you're interested in what the planets used to look like, say 10 million years ago or 20 million years ago. So because of the chaotic dynamics, you slowly get a diffusion in the possible orbital space that each planet could have explored over time. This is especially true in the inner solar system. And so this is a plot from a 2008 Lascar paper showing the probability that Earth has reached a certain maximum eccentricity over a given time scale. So there's lines written for the next 50 million years, 100 million years, all the way up to the next 5 billion years. And you can see that it kind of resembles a Gaussian. It turns out it's a Rice function, but that looks kind of like a Gaussian. And it just spreads over time. And there's a zoom in on the low probability events, the events that have probabilities of a few percent. And so what you see is that there's effectively 0 probability for Earth to get to an eccentricity of 0.1 in the next billion years. But that probability starts to grow because, again, chaotic diffusion causes the possible parameter space that Earth can explore to just slowly move outward over time. And you can see after 5 billion years, there's not a 0% chance. It's about 2%. And so that's kind of interesting, but there's nothing dramatic that happens when Earth reaches an eccentricity of 0.1. But you can also play this game for other planets. And the most interesting one is Mercury. So in Mercury's case, first of all, you're starting with a higher eccentricity. The eccentricity of Mercury today is around 0.2. And it also diffuses faster. And what you see is that now, instead of looking at eccentricities of 0.1, we're looking at eccentricities of 0.7, 0.8, 0.9. These are like very extreme orbits for planets. And we see that the probabilities are not 0. They're not huge, but they're of order 1 to 2% that Mercury will hit an eccentricity of 0.7 in the next 5 billion years. And when that happens, Mercury is no longer not interacting with other planets. It's making close passages near Venus. And it turns out that if you look at the details of these simulations, you find that there's a 1% chance during the remainder of the sun's main sequence life that Mercury will become eccentric enough that it will either hit the sun or Venus. And so it's not guaranteed that we will have our 8 planets for the remainder of the sun's lifetime. And so that's my general overview of chaotic dynamics, and we were interested in how long you can believe simulations to try to figure out what Earth's orbit has done in the recent geological record. And so what we did is we back integrated 100 systems with nearly identical conditions, and we just measured the standard deviation amongst those 100 systems as a function of time, and we got an answer that agrees with the previous literature that you hit 10% uncertainties at about 70 million years, 72 million years. And so this was kind of the state of the field 15 years ago. But then Lascar, I should have Lascar's name somewhere written in here, but I don't have it written here. But Lascar realized that it's not just the planets that can matter. Of course, there's other objects in our solar system beyond the planets. And I mentioned the asteroid belt as well. If you just include 5 of the most massive asteroids in your simulations, you find that chaotic diffusion is much faster. And the reason for that is that amongst the asteroids, chaotic diffusion is faster, and that quickly bleeds to the planets. So 2 systems might feel slightly different accelerations from the most massive asteroids, Sirius and Vesta, compared to the other system, because those asteroids have moved to slightly different positions. And very quickly, you blow up your uncertainties very quickly, and you introduce kind of a seed uncertainty. And after tens of millions of years, that manifests to reaching this kind of gray region where you can stop believing individual simulations. You reach it about 5 million years faster. So you shorten the time horizon of your simulation's predictability by about 10%. So that made us kind of wonder, asteroids exert pretty small accelerations on the planets. And amongst 2 simulations, it's not like one doesn't have asteroids and the other one does. It's just that they're in slightly different positions. So it's a really small difference in accelerations between those two hypothetical simulations that lead to wildly different outcomes. And I've always been interested in how passing stars affect the solar system because of my thesis work on the Oort cloud. So we started to wonder maybe other subtle effects like passing stars could affect the orbits of the planets. So we ran a set of simulations to see if that was the case. And so here what we did is we started our 100 simulations, and we just threw stars past, kind of like throwing darts at a dartboard, but blindfolded. Because you don't want to hit the solar system on purpose. And the stars, the rate that we threw stars past was simply based on the solar neighborhood, the mean density, the local velocity dispersion of the stars, as well as their mass function. And each one of those simulations was exposed to a unique set of potential field star encounters for the duration of the simulations, which was 80 million years. And what we found is that there's another effect. So initially, I should say that this dashed blue line, this includes both stars and asteroids. But if you take out the asteroids, you still have the same lines. That tells you that the stars are doing something important. But initially, the stars and asteroid simulations overlap each other. But then you see that the stars start to accelerate and reach this gray zone just slightly faster than the asteroids. And so what we found is that instead of 66 million years, you're now down to 61 million years. So you've basically shortened the time horizon or the ability of simulations to predict what has happened or what will happen in the future by yet another 10%. And this is kind of cool because with Gaia data, we've now been able to search for known encounters with the solar system. And one of these encounters, I talked about it earlier today at coffee, is with this star shown here, HD 7977. It passed near the sun 2.8 million years ago. And even with Gaia data, how close the star came is still fairly uncertain for our purposes. If you look at the median distance, is around 13,000 AU. But if you look at the 5th percentile closest distance, it came within about 4,000 AU. If you go to the 95th percentile, you're at 31,000 AU. So just to see how much the star could matter, we chose the more exciting one. And just we took our 100 systems, and we just threw this single star by them. We threw it by at 2.8 million years in the past. And we varied its stellar velocity and time of encounter based on uncertainties in its radial velocity. And then we looked at the outcome of our 100 systems, which are going to be shown here. And then we compared those outcomes with another set of 100 systems that were not subjected to that stellar encounter at all. And should have started this movie already because it takes about 50 million years for it to get cool. But I should say that This is not doing anything to the solar system 20 million years ago, because like a star that passed 3 million years ago can't do anything to previous epochs of the solar system, but it's basically, it's altering our interpretation of what the solar system could have looked like. So you're changing the conditions that could give rise to the solar system we see today. Now you can see after 40 million years, the ones with HD 797, you're starting to see significant differences between the isolated samples, or the isolated systems. And by 50 million years, it's quite apparent that this single stellar passage adds a large degree of uncertainty to the simulations. And so we're cherry picking results here because we're using kind of the closest possible encounter, but we're using it to just show that encounters can matter to our interpretation of what, our understanding of what the solar system did look like. And so, so you can see that there's just a broader swath of parameter space 65 million years ago that could have given rise to the solar system's current state. And this is for the Earth's orbit. I should have mentioned that. Now the question is, why do stars matter? Because although this star passed close-ish to us in the grand scheme of stars, it passed 4,000 AU away from the sun. The Earth and the sun are just 1 AU apart. They're different. Like the Earth should have seen maybe a few millimeters per second difference in velocity due to that stellar encounter than the sun. So even for this stuff, that's really small. And it turns out that it's not a direct perturbation on the Earth that matters. The further away you get from the sun, the more important the stellar encounters become. Because what matters is the difference between what the sun feels and what another object feels. And the bigger the distance between the Earth and the other object, the bigger the difference, the more important that passage is going to become. And so what I've done is I've made our same eccentricity plot for Jupiter, both with this passage and without this passage. There's 100 different systems shown here, and their lines just overlap completely. This is at T minus 3 million years, so just running backwards in time. This is just after the passage happened. But if you go to 40 million years ago, now you can see that our systems that were subjected to the passage, Jupiter is in a much broader range, has explored a much broader range of space, of parameter space, than the ones without the passage. And the interesting thing about this is the isolated system simulations that don't include stars, that just include the planets and even asteroids. Effectively, the giant planets are like metronomes of the solar system. Their precession frequencies just don't really change much at all. But the stars cause you to have to relax that assumption. You can do the same thing with Saturn. So here's just after the passage occurred, and here's tens of millions of years later. So you can see that the 100 systems with Saturn that are exposed to the passage, they're exploring, there's a much broader range of possible Saturn orbits than the ones over here. And so what happens is, what you find is that the stars don't directly perturb the Earth. What they do is they just exert a slight amount of jitter onto the giant planet's orbits. Because the giant planet's orbits perturb the inner solar system, that jitter eventually, it takes a while, but that jitter eventually bleeds to the inner solar system. And this is what accelerates the chaotic diffusion of the inner planets. So this was all part of a paper we wrote last year, showing that we should be more uncertain than we thought about our predictions of what Earth's orbit used to look like, because you have to consider stars. But all those simulations were performed on time scales of tens to really 80 million years. But the solar system has been around for 5 billion years and will be around for another 5 billion years, give or take a few hundred billion years. So I mentioned before that throwing stars past the solar system is like throwing darts at a dartboard if you're blindfolded. And so if you just throw darts for 80 million years, you're probably not going to get a bullseye. But if you throw for 5 billion years, you're probably going to come much closer to getting a bullseye. And so this becomes important because there's this other prediction of simulations that were run for isolated solar systems, showing that it's not guaranteed that the planets are going to be stable forever. And so again, this is just for isolated systems. We found, or not we, Jacques Lescar and other people have found that there's about a 1% chance that Mercury will will be involved in a collision in the next 5 billion years. So we wanted to know, how can stars change this? And if so, how do they change this? And so we wanted to run analogous simulations of this, but for 5 billion years. And so that's what we did. And so our simulation setup was just like before, except instead of generating, these are low probability outcomes. So instead of using 100 systems, we used 1,000 solar systems. Again, nearly identical initial conditions. The planets are just shifted by order of centimeters. And then each of our 1,000 simulations were exposed to a unique set of stellar encounters where you just fly stars past the sun. Oops. And most of those stars are not going to do much. But like I said, over time, you're more and more likely to get one that comes close to the planets. And that's what we're kind of interested in. What are the outcomes of those types of events? And then you want to see the net effect of the stellar encounters, so we repeated our simulations in isolation as well. And then you just compare the outcomes. So the takeaway from that, or the punchline, is that we did find that stars can trigger instabilities, which this is known. I mean, if you throw a star 1 AU away from the sun, something bad's going to happen. But it turned out that you didn't have to get within 1 AU. So this is an example simulation where a unremarkable low-mass star, 0.25 solar masses, passes within 55 AU of the sun 1.3 billion years from now. And on the left plots over here, I have the perihelion and aphelion. I didn't explain what aphelion is, but it's the distance of furthest approach from the sun. And of each planet is shown here. So the further those two lines are away from each other, the more eccentric the orbits are. So I have that shown for Jupiter, Saturn, Uranus, and Neptune, as well as Pluto up here. And then I have a separate plot for the inner solar system, so Mercury, Venus, Earth, and Mars right here. And you can see the effects of the stellar encounter immediately. So Pluto is immediately knocked out of its resonance with Neptune, and it quickly doesn't get ejected. It gets trapped in the Oort cloud in this particular simulation. And so that happens almost immediately after the encounter occurs, but then there's a more delayed effect. So the delayed effect occurs, even though, and you can see that there's a clear change in the eccentricity oscillations of the planets as well. But the delayed effect starts to happen about 30 million years after the stellar encounter. 30 million years after the stellar encounter, suddenly Mars's eccentricity shoots up to the point where it gets ejected. And then another couple hundred, or 200 to 300 million years after that, Mercury and Venus's eccentricities start to increase until they collide with one another. And then finally, 400 million years after the encounter, Venus, or the product of Venus and Mercury, hits the Earth. And then Earth finally winds up on this wildly bad orbit for life. Its semi-major axis moves into 0.8 AU, and its eccentricity is fluctuating by huge values. I'm guessing like 0.5 or something like that. So that would be bad on multiple levels for life on Earth. So I obviously picked a dramatic example to show you. But we did find that, that stars can be important. And then a natural question is, how do we decide if a stellar passage is important? In our previous work that looked at the detailed predictions of Earth's past orbit, remember, we tied all that to perturbations on the giant planets. What we found is that the giant planets' orbits scaled with the impulse gradient from a stellar passage. And I'll explain what that is in a second. So this is true. So that the impulse gradient depends on what's called the impulse approximation, which assumes that for the time scale of your stellar encounter, you can assume that the position of the star and the planet are fixed. We're very, very far from that, because the time of the stellar encounter is way longer than the planet's orbital period. But in spite of that, we found that it scaled well with this. And the impulse gradient is proportional to the inverse square of the impact parameter. So it rises steeply as you get to closer and closer passages. And the impulse gradient is effectively this. So you imagine you fly a star past the sun and the Earth. The sun's going to feel some net velocity impulse due to that stellar encounter. And since the Earth is in a slightly different position, it will feel a different impulse. And so the impulse gradient is how much that impulse changes as you move away from the sun and get closer to the stellar encounter. And so our 1,000 systems that we modeled only had there were only 6 cases with planetary losses or collisions. But 5 of those 6 unstable systems had an impulse gradient. If we look at their most powerful stellar passage that they underwent, that impulse gradient would have ranked in the 96th percentile or higher of all of our 1,000 cases. So the odds of that just being a coincidence are very small. In addition to that, I should say that this is just planetary collisions. We found many Pluto instabilities, and those were definitely as dependent on impulse gradient as well. In total, about 40 of our systems lost Pluto, which is pretty cool because if you just run the solar system isolated, Pluto is, you never see a Pluto instability. And so we found that Pluto's stability is not guaranteed. And these are systems that lost Pluto. Another 1% had Pluto kicked out of its resonance with Neptune. And so based on this, we're stuck with analyzing six instabilities. We wanted more than that. And so this is a distribution of the maximum impulse gradient that we recorded. So this is the percentile rank from 0 up to 100. So this is our most powerfully perturbed system. This is our most weakly perturbed. And this is the maximum impulse gradient. And this is measured in meters per second per AU. So you move 1 AU away from the sun. How much is the difference in meters per second between the Earth's impulse and the sun's? And so we just looked at systems. So basically, we just generated encounters until we would get an impulse gradient that fell in the 95th percentile of this distribution. And that basically corresponded to impulse gradients that were higher than about a half a meter per second per AU. So stuff in this range right here. And we generated 1,000 different types of these encounters, and we exposed 1,000 different unique realizations of the solar system to these. And we chose the encounter time at random because we don't know if that encounter is going to happen 2 million years from now or 2 billion years from now. And we integrated all systems up to an effective time of 5 billion years. And we found that these 95th percentile encounters matter quite a bit. We generated over 100 systems that went unstable with this. And now using these results, we could actually characterize what happens when a planetary system when our planetary system is destabilized by a stellar passage. We found that some planets are more likely than others to be to be unstable. And so what you're looking at here is you're looking at the relative instability rates of planets. So this is amongst all of our systems that went unstable, which planets are lost. And you can see that Mercury, just like for isolated systems, Mercury is the most likely to be lost. If you have a system that goes unstable, almost all the time, 97% of the time, you'll lose Mercury. And that's a result that's consistent with internal instabilities as well. The difference between our simulations, though, and internal instabilities, when I say internal instabilities, I mean isolated systems. For isolated systems, Mercury is typically the only one you lose. I mean, almost always. But we find that that's not the case. If you lose Mercury, about half of the time, you're going to lose at least one other planet. And that other planet is typically Mars. But it doesn't have to be. It can be one of the ice giants. It can be Venus and Earth. So this is very different from internally driven instabilities that are just due to the internal dynamics. And so for stellar perturbed systems, the instability is much likely to kind of cascade through the solar system and affect other planets as well. And looking at our unstable systems, as I said before, the main way that if I go back here, you can see that the inner solar system is much more sensitive to the effects of stars than the outer solar system, even though the inner solar system is closer to the sun. And again, the reason for that is that the way it works is the inner solar system kind of jiggles the giant planets, and then that excitation then bleeds into the inner solar system. And so we had a bunch of outer solar system architectures that were affected by the stellar encounters, and we wanted to see what actually mattered. And it turned out that most of our instabilities came when Uranus and Neptune were moved around some. And so what I mean by that is if we look today at the ratio of Neptune's orbital period to Uranus's orbital period, that ratio is 1.96. It's very near the 2-to-1, their 2-to-1 resonance. And so this dotted line is where all of our systems started out at. If you move that ratio, so when you fly a star past, it's likely to jostle Uranus and Neptune a little bit. That ratio is going to change a little bit. If it moves inwards or outwards just a little bit by 1% or so, not too much happens. Your instability rate is still like 1 or 2%, not too different from today. But if you go past a ratio of 1.98 and get close enough to the 2 to 1, your instability rate goes from a 1 or 2% up to about 60%. And again, it's not Uranus and Neptune becoming unstable. It's typically Mercury and Mars sometimes too. And we don't know the exact mechanism, but I'm fairly certain it has to do with what's called a secular resonance. So this is what's called a mean motion resonance when the two orbital periods are in resonance, but then you have these precession frequencies. Those can be in resonance as well. So currently, Uranus's precession frequency is slightly less than Jupiter's. It's about 3 arc seconds per century, and Jupiter's is 4.25. As Uranus approaches that 2 to 1 resonance, its precession frequency goes up and up until it eventually gets very close to or even matches Jupiter's. And so that basically, that effect amplifies Jupiter's perturbations on the inner solar system. And we think that that is what drives this huge increase in instability. If you just nudge them a little bit closer to their 2 to 1 resonance. Now, if you nudge them a lot, you still get large instabilities too. But once you get over to here, you're really destroying things. But it's just, the ramp up is very asymmetric if you just shift this ratio a few percent. So we think that Uranus's and Neptune's proximity to their 2 to 1 is a source of instability in our solar system. The other thing that we saw is that has to do with the timing of the instability. So I mentioned before that isolated solar systems can go unstable on their own, but that effect takes a long time to occur. Typically, if you run an isolated solar system, you don't see any examples of instability until about 4 billion years from now, and the probability rises dramatically. For our systems, where the instability is driven by a stellar encounter, there is really no strong time effect. The chances of a strong stellar encounter in the next 100 million years, if you have a strong stellar encounter, it could occur 100 billion years from now, or it could occur 3.2 billion years from now. And so the instabilities due to stellar encounters are pretty much uniformly distributed in time. And the probability of an internal instability doesn't become higher until about 4.5 billion years from now. And so this other channel of instability that involves stars, it has a slightly lower probability, so it's about 0.5% of a percent. But this other channel is the much more probable mechanism for the next 4.5 billion years. The internal instabilities won't happen until the final, say, 10% of the sun's main sequence lifetime. And so basically, we've shown that this other channel of instability is the most likely one for the majority of the sun's life. So then I have a few minutes left. We can talk about fun tail cases with the Earth, too. So what you're looking at here, you can also look at low probability examples of what the Earth could have done. So here's a plot of the reverse cumulative fraction of systems, or of the maximum eccentricity explored by Earth. And so if you run an isolated solar system, Earth's eccentricity is very unlikely to get above 0.08, 0.09. Here we see that there's about a 10% chance that Earth's eccentricity gets above 0.1. And there's a 4% chance that, sorry, this is for our, these are not exact probabilities. Anyways, but there's you get this huge tail case out to high values of Earth's eccentricity that are never seen in isolated solar systems. And so even though Earth has a very small probability of being lost, it can still do cool things. So the actual probability of losing Earth from a solar system is only about 0.06%. So 1 in, 5,000? Something like that. Or 2,000? I don't know. But just because you don't lose Earth doesn't mean it escapes scot-free. So Earth is a collision sink for other planets that are more easily lost, in particular Venus and Earth. So there's about 1/4% chance that Earth will be either ejected or suffer a planetary collision during the main sequence lifetime of the sun. And then there's still other things that can happen to Earth. It might not be involved in a collision, but its eccentricity can still be excited. And there's about a 0.3% chance that Earth's orbital eccentricity will increase so much that Earth's insolation, average insolation from the sun, will increase by 2% or more. 2% sounds small, but that's about 10 times larger than the insolation changes due to normal eccentricity fluctuations that Earth would experience in isolated simulations of the solar system. So to conclude, The giant planets kind of act like a dynamical link that can allow passing stars to influence planetary dynamics down to the inner AU of the solar system. The net effect of this is it's harder to use simulations to predict what the Earth is going to do or any other planet is going to do in the future or the past. And it also meaningfully increases the solar system's, I should say decreases, meaningfully decreases the solar system's stability. So Pluto's instability rises from, or instability probability rises from 0% up to 5% when you include stars. And Mercury's increases from 1 to 1.5%. Those aren't, order of magnitude changes, but the cool thing is that if you're interested in what's likely to happen for the next 4.5 billion years, this type of instability, that's one that's caused by stars, is actually much more likely than one that's driven just purely through planet-planet internal dynamics. And the other thing that's interesting about these instabilities is that they tend to be more global. So ones caused by stars are often about half the time involve losing 2 or more planets. Ones that are that just occur in isolated systems, you typically just lose Mercury and that's it. And then we also found that there's about a 1 in 400 chance that Earth will be ejected or hit another planet during the lifetime of the solar system. With that, I'll take any questions. And thanks for your time.
That was great. We must have some questions, Brian.
Based on our knowledge of the solar system, can you say anything about what might have happened in the past?
No, so that's one thing I'm actually interested in. Let me escape here. This doesn't directly involve stars, but there's this chaotic diffusion that I talked about before with the eccentricities explored by the terrestrial planets. And so the eccentricities of the inner planets diffuse over time. And what we typically do when we run simulations of the formation of the terrestrial planets is we use the modern day eccentricities to constrain that process. You try to produce a set of rocky planets that have the same eccentricities as today. But we know that there's a degree of angular momentum transfer between the outer planets and the inner planets. And what I'd like to do is, how confined do you have to make the original eccentricities of the planets, say 200 million years after the sun formed, to match what we see today? Because there is this diffusion. That's not really directly answering your question, but the only thing I can say is I don't know. is the short answer. There's no that you can. Your answer was, is there anything else we can do to constrain it, right?
Right. Is there anything we know now that can constrain what stellar encounters might have?
Oh, what stellar encounters? So the best we can do, I think, right now is just with Gaia data, and so that HD 7977 encounter is the closest one we have in the last 5 to 10 million years from Gaia data, and that's by far the closest one. Now, I don't know how complete that set of encounters is out to 10 million years in the past, though, either. Especially at the low mass end, there could potentially be other ones there as well. Because you also need the radial velocities as well.
So I guess I have a two-part question. The numerical aspects of this are really hard. So can you reassure me that this sensitivity to initial conditions is really physics and not a numerical artifact?
Yeah, I mean, I can reassure you in that I'm not the only person that has done this sort of stuff, and there's been lots of different algorithms that have been used, and these are all done with symplectic integrators, which the energy and angular momentum error are bounded with. Matt knows about this a lot more than me. Are bounded with time. Now, but I mean, you do get some initial spike because the integrators all have uncertainties, but those uncertainties are bounded with time. And the thing that made this taxing to do was we wanted to be able to integrate Mercury through high eccentricity phases, but we also wanted to be able to integrate close encounters between bodies. That required using an integrator that was performed in democratic heliocentric coordinates, which aren't the greatest at integrating through low pericenter passages. So we had to integrate with a 1.5 day time step for 5 billion years. And we tested that just through hypothetical Mercury eccentricities to verify that it still conserved energy and angular momentum to acceptable levels.
Thank you. The second part of my question is, when these stars come by, is there tidal deformation of the sun that changes its quadrupole moment? And does that perturb the orbits enough to be important?
I mean, there has to be probably some tidal deformation, but I wouldn't think that there would be enough for that to be more important than like than the gradient and impulses that you get throughout the solar system. But the quadrupole of the sun is important in general for the precession of the planet's orbits, but I don't think it changes by. I'm saying I don't think, but I never did it either. So my instinct is that it wouldn't change enough to alter the statistics of the dynamical outcomes. But that's just based on gut feeling too. I don't have a definitive answer for you. Sorry. Yeah.
Sort of stepping out the solar system then, thanks for the talk by the way. So the early formation of stars and planets are much more clustered environments.
Yeah.
I wondered if you postulate the possibility that most of the free-floating planets that we're now seeing were caused instead of by internal planetary scattering events, but instead by stellar encounters.
That's a great idea. There's a paper that's going to be out about that. But I think it depends on the density of the star cluster, though, too, and what fraction of planetary systems are born in what density environments. But I think certainly you have to have instabilities that are triggered by stellar passages. But I'm hesitant to say that they are. I mean, I would love my papers to explain everything, but I'm hesitant to say that that's like the dominant source of free-floating planets. But just because there's a lot, I presume that there's a good fraction of planets that are formed in low-density environments where that wouldn't be like the modal outcome.
So I kind of wanted to ask a related question, which is, it seems like the encounter rate between sort of stellar passages is kind of an important factor,
sure,
and
yeah.
you just accumulate them, and you were showing that the probability grows linearly in time with that encounter rate. So is there like a finite encounter lifetime that a solar-like system can survive, like X number of encounters, or is it kind of critical that you need this diffusion time also?
Yeah, that's true. I still think I talk about the diffusion time in terms of the simulation's predictability, but I don't know how important that is for the actual instabilities. You do require a diffusion time for the excitation in the outer solar system to bleed into the inner solar system, but still that we looked at the delay in times between the encounter and the actual instability, and the median time was of order, I want to say 400 million years. Which is long, but it's a lot shorter than the age of the solar system. So I think it really is just a steady accrual of encounters. But this is a random thing. So you would think you just leave the solar system sit around long enough. It's going to be destabilized, which people have done that, like because the solar system becomes a bigger cross section after the sun becomes a white dwarf because the planet's orbits expand, and somebody's done that work. Zinc et al. And they found, I think, 20 billion years. The hole in that work is that we're going to collide with Andromeda in, 5 billion years or something like that? And that's going to change the stellar environment completely, too. So, yeah.
I wondered if this constrains the architecture of other systems, systems like TRAPPIST-1 with densely packed planets also be more chaotic over gigayears?
I would think so, but so I would think for a given perturbation, TRAPPIST-1 would be more susceptible to instability, but I don't know how well constrained the outer parts of TRAPPIST are, if they are at all. But I mean, we do have planets at 30 AU, which just makes us a bigger target too. But I would think very widely separated planets would be potentially very more susceptible to this than the 1% probability that the solar system is.
Hi, thank you for the great talk. I was just wondering if I remember correctly, the same way you were showing your inclusion of the star that from Gaia data that passed, I know, billions of years ago, right?
Yeah.
If I remember correctly, there's also like a star that's predicted to pass like within the next million. Have you
Yes.
looked into that as well?
Yeah, we have. I can't remember the name of that star now.
It's, I think, Gliese 710 or something.
Yes,
like that.
yeah. So I want to say that one's encounter distance is around 10,000 AU. Do you know off the top? It's
No, I
not as
don't.
close as HD 7977, and I think it's less massive. I want to say it's 6/10 of a solar mass, maybe. But it can matter quite a bit for the Oort cloud and long period comets, which I'm also interested in. But I think it's beyond the distance where it'll matter for the dynamics of the solar system. So I think the cutoff, the crude cutoff, because velocity and mass matter as well, but the crude cutoff is around 10,000 AU encounter distances.
Let's take one more question.
Thanks. I actually have two, but you can choose which one to answer. So it seems to me you could use this to determine I want to put this correctly, the maximum density below which you can get a stable solar system. So above some density of stars, you're going to have too many encounters.
Yeah.
So it seemed, I don't know if that's possible with your current tools, but it seems you might be able to do that. The other question is, presumably when you are starting to form the solar system, you don't have all of these resonances and the masses are a little more spread out. So at before some point, it doesn't matter.
Right, yeah.
And so it would be interesting to know at which point, because that might mediate the effects if you have a lot of young stars with planet formation and they are dense, but it takes a while, so there could be a complicated interplay.
Yeah, that's true. And there would presumably be higher numbers of small bodies, which could damp things out, any excitation too. Yeah, that's true. I hadn't thought of that. I don't know that. I don't have a feeling for what that point is, though. Yeah, that's a good point. Yeah.
Well, let's thank Nate again for a great talk.